Hello everyone and welcome. My name is Jason Gregerson and this video is a exam review for the MA 3520 Midterm Exam 1. Alright, through the process of this exam review, what I'm going to do is I'm going to post some questions here. I'm going to suggest that you pause the video and then you work through the problems yourself. And then after that you can unpause and see if your solutions match my solutions. But I strongly encourage you to pause the video and see if you can work through the problems on your own first. The first problem says given this differential equation, d dt equals 2 minus a over 10, and this initial condition, a of 0 equals 5, go ahead and see if you can work with this initial value problem. Specifically, see if you can classify it by order, linearity, and autonomy. Then, given the slope field to this differential equation, which is given here to the right, see if you can approximate a of 3 and a of 200. And then see if you can use your numerical approximation to a of 4 using 2 steps of Euler's method. All right, see if you can pause the video and work through those problems. All right, now let's see if our answers agree. I'm going to start off here and classify. I have a first derivative here, so this is a first order differential equation. Because that first derivative is just raised to the first power, it's not being multiplied by a, and it's not the argument of a nonlinear function. And the same thing with the variable a over here, the dependent variable, since it's just raised to the first power, not the argument of any nonlinear functions, not multiplied by any of its derivatives. This is going to be a linear differential equation. And because there's no t's on the right-hand side, because there's no independent variable on the right-hand side, we know this differential equation is of the form dA dt equals just a function of a, and therefore, yes, it is autonomous. All right, now because it's autonomous, that already gives us some information here. That means we can see that along any horizontal line, we see that the slopes are not changing. There might be equilibrium solutions. Equilibrium solutions occur when the derivative is equal to 0. So I might take 2 minus a over 10 and set it equal to 0 and see what values of a satisfy that. If I added a over 10 to the right-hand side and multiplied by 10, I would get a is equal to 20. And sure enough, I can see a straight line solution here. And that would allow me to draw my phase portrait, where I draw a vertical line, I identify the equilibrium solution, and then I determine if solutions are increasing or decreasing about that equilibrium solution. In this case, I have a stable equilibrium solution at a equals 20 because the solutions about that equilibrium solution are tending towards that equilibrium solution. Next, for the graphical approximations, well, since my initial condition says a of 0 equals 5, I start at t equals 0, a equals 5, this point right here, and I sketch out my solution. If I follow the slope lines, I can sketch what this specific solution looks like. Then to approximate a of 3, I just look at when t is equal to 3 and see at what height I'm at on my plot. I would probably ballpark this to say maybe 9. A of 3 is approximately 9. And then what about a of 200? Well, I can't go out to t equals 200 in this graph, but I know that my solutions are increasing, and I have an equilibrium solution at 20. Therefore, I expect the long-term behavior of my solution to tend towards 20. So I would say this is approximately 20 in this case. And because it's autonomous and I have those equilibrium solutions, it really does allow me to determine the long-term behavior. I can look at the limit as t goes to infinity of various solutions depending on where I start. All right, next we have to use Euler's to approximate a of 4. So to do this, I might set up my table. My table that I like to use is I'll have some starting point. I know I can calculate the slope at that point by using the right-hand side of that differential equation, which is 2 minus a over 10. Then I'll need a step size. In this case, because I'm starting at t equals 0 and going to t equals 4, I'm traveling a distance of 4 in 2 steps. Therefore, my step size, my h value, my d of t in this case, should be 4 minus 0 over 2, which is going to be a value of 2. Then my last column is going to be the change in the dependent variable, the change of a. And to calculate that, I just take the slope times the step. So my slope times my h value should give me my delta a. So in this case, I'm starting out with points. Notice my points here are t comma a. So I might just write that down so I don't get confused. Well, my first point is the point 0 comma 5. So then I plug this value into my slope. I got 2 minus 1/2, which is going to be 1.5 or 3/2. I have a step size of 2. I multiply those values together to get a delta a of 3. I was at the point t equals 0, a equals 5. Now I'm at the point 2 and 8. From here I plug this new point value into my slope. From here I get 2 minus 8 over 10, or 0.8. In this case I'm going to get 1.2 is my value here. And since my step size is staying the same at 2, I get 2.4 for my change of a. Now I've gone over another 2 in the t direction, so I'm at t equals 4. And it looks like 8 plus 2.4 should be 10.4. So in this case, I would say a of 4 is approximately 10.4. And that does seem to be relatively in line with my plot. So I'm pretty happy at that point. A couple notes here, just notation. A of 4 is equal to 10.4. However, if I kind of identified my points here, this would be t sub 0, a sub 0, t sub 1, a sub 1, and t sub 2, a sub 2. So my a sub 2, my second Euler point here, is also the value of a when little t is 4 and is equal to 10.4. So on the exam, I might ask you for either notation, and you should be able to understand the differences there. All right, that's this first part where we have a differential equation. We've explored it graphically, we've classified it, explored it graphically, and numerically. All right, we'll scroll down here. We'll look at another graphical differential equation. So there's some differential equation here, and this differential equation leads to this, this slope field. And so the first question might be, is this thing autonomous or non-autonomous? We can tell if we look at the differential equation, but we should be able to get a sense by looking at the graph as well. In this case, we can see that along any horizontal line, those slopes all look the same, so I would say that yes, it is autonomous. And then we should be able to identify equilibrium solutions. Here it looks like I have one at y equals 2, and maybe y equals 0, so I have 2 equilibrium solutions. And the thing I might want to do is consider the long-term behavior of solutions that satisfy certain conditions. For instance, if y of 0 equals 1, what would the long-term behavior be? Well, for this solution, the limits as t goes to infinity of my solution would tend towards what? Well, if I started at y of 0 equals 1, it looks like my solution would tend towards that equilibrium solution at 2. If I started at some other value, if y of 0 is equal to 1.99, right, and you up here, it would still tend towards that value of 2. However, if I started at y of 0 equals 2.01, well, then the limit as t went to infinity of y would be infinite. It would tend towards infinity. That limit would not exist here. Okay, so there's a variety of questions we could ask about this. One question might be, where can I start? Y of 0 equals c, right? What values of c would lead to maybe finite solutions here? Which ones would not tend to infinity? In this case, I can see that as long as I start in between this region from 0 to 2, my solutions would be finite. However, also at y of 0 and y of 2, I would also have finite long-term behavior. So in this case, my answer would be from 0 to 2, making sure I use square brackets here. These should both be square brackets because y of 0 equals 0 or y of 0 equals 2 would also lead to finite long-term behavior. All right, so again, we've looked at a differential equation, we've classified it, we've explored it numerically and graphically. What about analytically? We have 3 different analytic techniques. We have separation of variables and the first order linear method. So here's my same differential equation. We know this differential equation is separable, and it's also a first order linear differential equation, so I should be able to use the first order linear method. So this would be a great time to pause the video and see if you can solve this differential equation using both techniques. Go ahead and pause and try now. All right, let's take a look together. We're going to start with separation of variables here. To separate the variables, I'm going to divide through by the entire right-hand side. I'm going to get 1 over 2 minus a over 10. From there, I'll feel like I'm multiplying through by dt. We know that's not exactly true, but we can kind of treat it like that. So that's me separating the variables. From there, I'll integrate both sides. Integrating on the left-hand side, well, I see an a to the first power in the denominator, and boy, that makes me think of the natural log of the absolute value of 2 minus a over 10. So that might be my initial guess. However, I always want to check myself with differentiation. If I took the derivative of that, if I took the derivative of this, I would get 1 over 2 minus a over 10 times the derivative of the inside function. The derivative of the inside function would give me a negative 1 over 10. That means I need to modify my guess by a negative 10 to cancel that factor. Integrating on the right, I'm getting t plus some constant, which I'll call c sub 1. From here, I need to solve for a. So I'll divide through by negative 10 to get negative t over 10 plus some new constant c2. From here, I'll take the exponential of both sides to get some new constant c sub 3 e to the negative t over 10, using my exponent properties to simplify that. From there, if I added this to the other side, subtracted over the c3 content, I would get 2 minus c sub 3 e to the negative t over 10 equals a over 10. And lastly, I would multiply through by 10 to solve for a. Now I'm going to write that as a equals 20, and then plus c4 e to the negative t over 10. In this case, I multiplied through by 10, and I consolidated not only the 10, but also the negative sign into that constant. And there may be some cases where WebWork will want you to consolidate all of your constants, including the sign, to write something as plus one single constant. So this would be my final solution using separation of variables. What about the first order linear method? Well, my first step in the first order linear method is to put my differential equation in standard form. So in this case, I'm going to add the a over 10 to the other side. Let's write it in standard form like this. In this, I can identify my coefficient that I'm interested in as 1 over 10, the coefficient of the dependent variable term, which means my integrating factor should be e raised to the integral of 1 over 10 dt, or e to the t over 10 power. From here, I take my differential equation standard form, and I multiply through by my integrating factor. Then I know that the left-hand side will always simplify to just the derivative of the dependent variable times the integrating factor. And this should be equal to the right-hand side. From here, I need to integrate both sides with respect to t. On the left-hand side, the integral of the derivative yields just a e to the t over 10 power. Integrating on the right, my constant comes out front. Integrating an exponential is pretty much an exponential, but here I would divide by that extra constant. In this case, that would result in multiplying by the reciprocal to give me 20 e to the t over 10 plus some constant, call it c1. And lastly, I'm going to multiply through by e to the negative t over 10 to solve for a. That will leave me with 20 plus some new constant, e to the negative t over 10. And apart from the names of my constants, we can see my two solutions match, which of course they should. So that calculates completes the first order linear method. Now what could I do with my solutions? Well, if I want, I could calculate a of 4 if I knew that some initial condition was a of 0 equals 5, and then I could always calculate the error of my Euler approximation. So I could take either solution and use my initial condition. A is 5 when t is 0. This would lead to this equation, and therefore my constant would be negative 15. This means my solution would be 20 minus 15 e to the negative t over 10. And then I could calculate a of 4 to be 20 minus 15 e to the negative 4 over 10, or 2/5. And then if I wanted to, I could plug this into a calculator to get an approximation, and then see how my numerical approximation was. All right, next, well, you look at our last analytic technique for solving differential equations, the method of exact equations. So it's another great time to pause the video, see if you can test this equation to ensure that it is exact, and then use the method to solve the differential equation. Go ahead and pause and try now. All right, let's take a look together. The ideas are exact equations have the form f dx plus g dy equals 0. In this case, my f function is this term and my g function is this term. And I'm really hoping that f is the partial derivative of some mystery function with respect to x, and g is the partial derivative of some mystery function with respect to y. But I don't really know if capital F exists. So first I have to test to see if the mixed partials would be equal. I'm going to calculate the derivative of the first thing with respect to y. In other words, calculating f sub x sub y if that thing were to exist. The derivative of this with respect to y is going to be 2x plus 1. Next, I calculate the derivative of the other piece with respect to x, calculating what might be the mixed partial if capital F exists. The partial derivative of this with respect to x gives me 2x plus 1. These two values match, therefore the differential equation is exact. That means there really does exist capital F such that f sub x, the partial of f with respect to x, is equal to this first term. And apparently the derivative with respect to y should be equal to the second term. If I know the derivatives, I can calculate the function by integrating with respect to x to get x squared y minus x cubed over 3 plus y times x, plus some mystery function potentially of y. That could be nothing, that could be a constant, it could be any function of y, and the partial derivative with respect to x would still bring me to this. So I just got to figure out what the psi of y thing is. To do that, I'm looking at the other piece and integrate that with respect to y to get x squared y plus xy plus 1/2 e to the 2y plus gamma of x, potentially some function of x. And now basically I have two different pictures of the same function f. I can put my pictures together. I have an x squared y term that matches the mixed term from the other side. I have a y times x. That term also has both variables and matches the other equation. Then I have an negative x cubed over 3. And lastly, I have some mystery function of y. I look to the other equation. I see this is the only piece that is just a function of y. That must be my psi of y. That's the last piece I need to form the function f. Now that's f, but my solution is f equals c. My solution is this equation equals constant. So that is the solution to my exact differential equation. All right, next I have another potentially exact differential equation. This is a great time to pause the video and check to see if it's exact. And if so, solve the differential equation. Go ahead and pause and check now. All right, let's run our check together here. So I'm taking this as my first f function, this is my g function, and then I do my check. The partial of f with respect to y is going to be x, and the partial of g with respect to x is going to be 2x minus 1 over y. All these are not equal, so far the differential equation is not exact. In this case, we might wonder, is there some mystery function u that I could multiply through my differential equation to make it exact? And so if I were to multiply it through by u, the new test to see if it was exact would be to take the partial with respect to y of the first piece, which would now be u times the quantity xy minus 1, and see if that's equal to the partial with respect to x of the second piece, which is now u times x squared minus x over y plus 1. Now, I need this to be true. I need to find a value of u that makes this true, and I can make any assumptions along the way that I want. I could, for instance, assume that u is just a function of x, or I might assume u is just a function of y. And I'm really not sure what to test at first. In this case, I'm going to start by letting u equal just a function of y. If we assume that u is just a function of y, and then we calculate the partial derivative of u times this thing with respect to y, well, then I would have to use the product rule. I would have to take the derivative of the first times the second plus the first times the derivative of the second, which in this case would just be x. On the right-hand side, if u is just a function of y, then it's a constant with respect to x, and my u would just come out front, and I'm really taking the derivative of the second piece with respect to x. The result there would be 2x minus 1 over y. From here, I would solve for du dy. So I would say du dy is equal to, and I might subtract this to the other side and divide through by xy minus 1. I would get u times the quantity 2x minus 1 over y minus u times x all over xy minus 1. And this will be beneficial to me if the resulting equation is just a function of u's and y's. And so far, I'm kind of nervous here because I still see some x's in this equation. But let's see what we get if we simplify a little bit. I can see that I can factor a u out of the numerator. In that case, my new numerator would be 2x minus 1 over y minus x. So 2x minus x is just x. So it looks like I would have x minus 1 over y. In the denominator, x times y minus 1. And here I might note that if I factor out a y in the denominator, I would get x minus 1 over y in the denominator. Therefore, that right-hand side really simplifies to just u over y. So, with my assumption u equals just a function of y, my differential equation is simplified to du dy equals u over y, which I can solve using separation of variables. In this case, I divide through by u, I multiply through by dy, I integrate both sides to get the natural log of the absolute value of u equals the natural log of the absolute value of y plus some constant. Exponential of both sides gives me some new constant times y. So it looks like y, if I just let the constant equal 1, would be a perfectly good integrating factor. Now that I know my integrating factor, I go back to the differential equation. If u is equal to y and I multiply through, I get x times y squared minus y dx plus x squared y minus x plus y dy equals 0. And this differential equation really is exact, and therefore I should just solve it by using my regular method. Apparently, if it's exact, this first term should be f sub x, and the second one should be f sub y. If I integrate the first term with respect to x, I get x squared y squared over 2 minus x times y plus psi of y. If I were to integrate the second piece with respect to y, I would get x squared y squared over 2 minus xy plus y squared over 2 plus gamma of x. Therefore, f should equal x squared y squared over 2 minus xy plus psi of y, which is y squared over 2. Setting this equal to constant yields my final solution. So in this case, the original differential equation was not exact. We had to figure out the right integrating factor to make it exact. We did this by multiplying through by u and rerunning our test. In this case, assuming that u is just a function of y, led us to a differential equation we could solve for u. All right, exact equations. And that really wraps up our analytic techniques for solving differential equations. After that, we got to some existence and uniqueness theorems for first-order differential equations. And we basically had two of these. One for the general differential equation. Any first-order differential equation can be written in this form, dy dx equals some general function of x and y. And then we had a separate theorem if we had a linear differential equation, in which case we could always rewrite that linear differential equation to look like this standard form. So our general theorem said that if our differential equation is written to a normal form, dy dx equals just some function of x and y, then there would exist a unique solution in some region around x sub 0, y sub 0, so long as f, and the partial of f with respect to y, the dependent variable, it was defined and continuous at x sub 0, y sub 0. So as a quick example, we might consider dy dx equals y to the 1/3 power divided by x minus 1. And say, does there exist a unique solution at potentially a y of 1 equals 2, for example? And before we look at the specific condition, we'll just do our test. In this example, my f function is y to the 1/3 divided by x minus 1. So whatever's on the right-hand side. And as I look at that, I might say what x or y values break f. In this case, only x equals 1 would break it, so x can't be 1. So in this case, with my first condition, I immediately know that there's no solution. There's no solution that satisfies this condition. However, I might look at another one and say, what about y of 2 equals 0? There's another condition. Well, because x equals 2, I know there would exist a solution. Yes, there exists a solution, but to determine whether that solution is unique or not, I have to check my partial derivative. The partial of f with respect to y is equal to, well, my 1 over x minus 1 just comes out front. I'm really taking the derivative of y to the 1/3 power, which is 1/3 y to the negative 2/3 power, which I could rewrite as 1 over 3 times the quantity x minus 1 times y to the positive 2/3 power. And now I'm saying what x or y values break this. Again, x can't be equal to 1, but now y also can't be equal to 0. So in this case, because my y value is equal to 0, I would say there's not necessarily a unique solution. So for the condition y of 2 equals 0, yes, there exists a solution through this point, but it might not be unique. So we'll slide this to the left here and say there exists a solution, but it might not be unique. Okay? And then if I had some final condition, if y of 3 was equal to 4, in this case the x value is 3 and the y value is 4, neither are a problem. So for this condition, there would exist a unique solution through that point. All right, so that was the general theorem. Now, if the differential equation was linear, well, then I can make a stronger statement. I don't have to check the y's in this case to see if they're going to be a problem because I just have y and y prime just because it's linear. So in order to determine if there's a unique solution at some condition t of 0 equals y of 0, all I have to check is a of t and f of t. As long as they're both okay and well defined at t sub 0, then there will exist a unique solution through that point. And not only that, but I actually know the entire domain of that solution. So for example, if I had the differential equation that was t dy dt plus 4y equals the square root of t plus 2, my first job would be to put this in standard form. I'd have to divide through by t. Dividing through by t yields this differential equation. And now I would just analyze a of t and f of t. A of t, t can't be 0 because I have t in the denominator. For f of t, t also can't be 0, but I also need to have non-negative zeros under my radical. So t in this case would have to be greater than or equal to negative 2. So then I can talk about the intervals where I know there does exist a unique solution. In this case, for instance, I know that I could have the interval that starts at -2 and goes to 0. Notice again I can include -2, that's okay, but I can't include the 0 value. Another interval would be from 0 to positive infinity. So then I might say, well, what if I had the initial condition that was y of -1 equals 10? In this case, because t is -1, I know there will exist unique solution through this point, and that solution will have a domain that is from -2 to 0. However, if I had another condition, y of 2 equals 4, in this case, there would exist a unique solution that satisfies the condition, but now I'm living in the other interval, so this solution would have a domain from 0 to infinity. All right, that really wraps up our existence and uniqueness criteria for first-order differential equations. Next, we'll focus on applications of differential equations. So far in the course, we've looked at several different applications of first-order differential equations. The four I want to focus on here is Newton's law of cooling, our population models, circuits, and mixing problems. Now, we have looked at Newton's law of cooling and whether we express our differential equation like this or we force a negative inside of that k, doesn't really matter. The idea here is that the rate of change of the temperature of some object was proportional to, in other words, equal to a constant times, the difference in temperature between the object and its surrounding environment. So T sub E here was the temperature of the surrounding environment. And we've looked through that model a couple times here, so we're pretty much going to leave it at that. Then we also looked at population models. We saw that there were different models that we could use to model populations. Exponential growth was a perfectly reasonable population model when there were no constraints to the environment. However, the logistic model also accounted for some sort of carrying capacity of the system. Written in this form, the value of m here was the carrying capacity. Capacity. And so far, one thing we can notice is all three of those differential equations have all been autonomous differential equations. So when we can find that carrying capacity is just to find the equilibrium solutions, and the upper equilibrium solution would be the carrying capacity of the system. The last two applications we talked about a little bit less. Circuits, where we use Kirchhoff's law, which states that the sum of the voltage drops around a circuit is equal to the electromotive force. And the voltage drops around that circuit could be caused by resistors or inductors or capacitors, and they each had a quantifiable voltage drop. And so that set up an equation that involves some derivatives, and we'll look at an example of that. The last application was mixing problems. Here we have some tank of some substance, some fluid mixed with some sort of other additive, and we had some concentration of that mixture flowing in, and then the contents was well mixed, and we had some outflow. And the concept behind this differential equation was the rate of change of the amount of stuff in the tank was equal to the rate flowing in minus the rate flowing out. And we'll look at an example of that. But we'll start with the circuits problem. So Kirchhoff's law basically states that the supplied voltage to the circuit, the E of t, the electromotive force, is equal to the sum of the voltage drops. Now you should note that E of t means it could potentially be a function of time. In a lot of our examples it won't be a function of time, but rather have a fixed voltage. Now in this case, I of t is the current through the circuit, E of t is the electromotive force, R is a resistor in this, which has a voltage drop that is equal to the resistor rating measured in ohms of that resistor, and times the current. And L is the inductor that's been placed into the circuit, and there's a measurable way for us to calculate the voltage drop across the inductor. It's equal to the rating of that inductor, L measured in henries, times the derivative of I with respect to t. Now the idea here is that we now know that the sum of the voltage drops, this is the voltage drop from the inductor, this is the voltage drop from the resistor, should be equal to the supplied voltage to the system. That sets up our differential equation. And this differential equation will be supplied if you need it in the exam. And so we have this basic starting point, and in any specific circuit, they are giving us the values of the inductor and the resistor, and they're giving us the value of the supplied voltage, and they're actually giving us some initial condition which says that basically that there is no current flowing until we flip the switch. So in other words, at time equals 0, there is 0 current. And then we need to set up and solve the differential equation. And all we're really doing is plugging in our constant values. So when L is 3, and R is 6, and E is constant 12, this yields the following differential equation. And once we write that out, we can see we have a first-order differential equation. It is separable, it is linear, and so we can certainly go through this and solve this. Not only that, but it's actually also an autonomous differential equation. If I were to write this in standard form by dividing through by 3, I would get this differential equation. If I were to write it in normal form, solving for di dt, I would get this. From here, I could see it's an autonomous differential equation with an equilibrium solution at I equals 2. If I start at values below 2, if I equals 0, for instance, I would have a positive value for di dt, so my solutions would be increasing. And if I started with an I value above 2, I would have a negative slope, a negative di dt, so solution would be decreasing. So in this case, because I'm starting at I of 0 equals 0, just by looking at that phase portrait and understanding this autonomous differential equation, I know my solution should be increasing to some limiting value of current equals 2. Now to solve the differential equation, we could just set up our integrating factor. In this case, our integrating factor would be e raised to the integral of 2 dt, or e to the 2t. After multiplying through by my integrating factor, the left-hand side should simplify to the derivative of my dependent variable times my integrating factor equals the right-hand side times my integrating factor. Integrating both sides of this should yield 2e to the 2t plus some constant on the right-hand side. And if I multiply through by e to the negative 2t to solve for I get I equal 2 plus some constant e to the negative 2t. And this should be my general solution. Note in that general solution that as t increases, that second term goes to 0, and my current should approach 2, just like I can see from my phase portrait. Now, if we can plug in our initial condition that says I is 0, when t is 0, I can see that c is equal to negative 2, and therefore my final solution would be 2 minus 2e to the negative 2t. And so this should be the specific solution that satisfies my initial condition. Lastly, we're going to look at mixing problems. Mixing problems, once again, we have some quantity of some stuff in the tank. For instance, we might say that our tank has some brine mix in it. That's a salt water mix. And we're concerned with our variable x here, which represents the amount of salt in the tank at any time. So we have a tank, we're pumping in a salt water mix, we're pumping out some mixed version of that. We want to figure out at any given moment how much salt is actually in the tank. So the concept behind a mixing problem says the rate of change of the amount of salt in the tank should equal the rate of salt flowing in minus the rate of salt flowing out. Now, what do we know about our inflow and what do we know about our outflow? The inflow tells us that we have a saltwater mix of a concentration of 0.03 kilograms per liter of salt. So we know the concentration of the inflow, 0.03 kilograms per liter. We know this inflow is coming in at a rate of 25 liters per minute. And so now if we want to think of the rate of salt flowing in, well, that's a rate of salt. That should be some kilograms of salt per some unit of time, maybe per minutes. And therefore, to calculate the rate of salt flowing in, all we're going to do is take the concentration, 0.03 kilograms per liter, times our inflow rate of 25 liters per minute, and we'll see that those liters are going to cancel, and the result is just going to be kilograms per minute, the rate of salt flowing in. In this case, if we wrote 0.03 as 3 over 100, we could then simplify by multiplying through that by 25 to get 3/4 kilograms per minute. Now what about the outflow here? Well, the rate of salt flowing out should be the same general process. It should be the concentration times the outflow. Well, the outflow in this case is also 25 liters per minute. But what about the concentration of the salt in the tank at any given moment? Well, that should be calculated by taking the amount of salt in the tank at any given moment divided by the total volume of the tank. Now I know the tank has 5,000 liters, and it's important to know because the inflow is 25 liters per minute and the outflow is the same 25 liters per minute, that we'll have a constant volume of 5,000 liters in the tank at any time. So I know the volume in the tank is 5,000. The concentration should be the amount of salt in the tank divided by that. Well, how much salt is in the tank at any moment? That's my variable x. So this should be x over 5,000 times 25 in this case. Now we can simplify this if we want, right? We know that we could rewrite this. We could cancel a factor of 5 to get 5 over 1,000, and then 5 over 1,000 should be the same as 1 over 200. So this should simplify to x over 200 kilograms per meter. And now we have this differential equation. dx dt equals 3/4 minus x over 200. And this is a first order differential equation. It's an autonomous differential equation. It's a separable differential equation. And we can solve it via any of those methods. In this case, we'll leave you to find your solution. I will give you the final version here. Notice that this will be the differential equation. We will need an initial condition, and that's actually also provided. They told us that 20 kilograms of salt is initially in the tank, so that would tell us that x of 0 equals 20. So we have the differential equation, we have the initial condition, and we can go through our solution process to find the amount of salt in the tank at any specific time. All right, that concludes this application, and that concludes this exam review. Thank you for your time.